Hello everyone, Namaste. I am Damodar Koirala and I'll be talking about the inorganic chemistry group D, which is titled as analytical and instrumental in the syllabus of Masters in Organic Chemistry of Trubhuvan University, Nepal. So basically I'll be making the series of slides that will be focusing on the group D of this inorganic chemistry, the master's level of MSc chemistry of Trubhuvan University. So make sure that you have pen and a copy with you to take some notes, because these are some very serious topics and you might want to take some notes while you are studying or preparing for future. Okay, let's begin. In group D of the analytical and instrumental, there are several topics, and this is the part of the syllabus that I copied and pasted. It has the two parts, which I have summarized in next two slides. In part one, it is the brief review of chemical analysis. And this part consists of titration, redox titration, complexometric precipitation, some of the common chemicals, the indicators and their mechanism. So this is the part one. And the part two is based on the instrumentation, their working principle and their applications. These are the list of the instruments that we'll be discussing by the end of this course. So whenever you get into this instrument part, make sure you know their working principle and their application for what they are used, and the instrumentation. Basically, the instrumentation means what are the components of the instrument? What is the instrument made up of? What are some of the good features of the instrument? What are some of the bad features of the instrument? For what purpose you can use it? And all sorts of questions related to those instruments. And in the inorganic chemistry, so I'm talking about the inorganic chemistry whole thing right now. This is the practical in the syllabus. I just want to share these practicals with you because, as you can see, all these practicals are related to the topics in group D that I'll be discussing. So the volumetric, they are all based on volumetric analysis. These are the 6 practicals in these slides, and there are 8 more in the other slide. These are all the practicals of inorganic chemistry. And as you can see, all these practicals are related to group D. And also in the group D, they are related to the part 1 only. So for the part 1, which is based on the titration, that part is going to be relatively easy because you all must be familiar with the topic titration since you're +2 science. You went into the depth in Bachelor of Chemistry, BSc. And now you'll be discussing those in theories as well as in practicals. So the beginning of this course will be relatively easy as compared to the second part of the instrumentation. These are the books for chemistry 501. The 501 is the inorganic chemistry. There are 19 books referred by the syllabus. And as these are the books for inorganic chemistry for the group D part that I will be discussing about, for that I think it would be better off if you have 2 of these books that I have highlighted, that the book number 9 and the book number 18. The book number 9 is the Principle of Instrumental Analysis by Skuz, and the book number 18 is the Bogle's textbook of quantitative chemical analysis. These books are very famous book and it's worth purchasing them. I believe you can also borrow them from the library. However, if you buy them, if you purchase them, then it will become handy in future when you work in the industries or when you plan to be a professor. And most of the uh, concept that I will be teaching are also based on these two books. However, I have also collected the information online and other resources. This is the tentative plan of the semester. This is the first semester of MSc Chemistry. I have separated the days into 13 different days for Group D. Today is the first day and we'll be discussing just the introduction of the titration and some of the terminologies. That introduction will will guide us for 3 other lectures, lecture 2, 3, and 4. Those are all based on titration. And then we'll have 2 different lectures, lecture 5 and 6 as an introductory lecture for the rest of the course. So the first highlighted box is the part 1 and other second highlighted box is for the part 2. So let's get into the introduction. So first, let's understand some of the significance of chemical analysis. I believe all of you are familiar with all this concept. So chemical analysis are basically used for chemical composition analysis, contamination analysis, material testing, chemical tracing, defect analysis, elemental analysis, in metal alloys analysis, in chemical regulatories, compliance testing, product deformulation, residue analysis, failure analysis, method development, and regulatory compliance. These are just some of the significance of chemical analysis. So this could be the main reason why we have to study the chemical analysis, because these all are related to the regular life activities and also in professional life. So whenever you think about chemical analysis, the chemical analysis can be done in 2 different ways. One of them is by using the instrument, which we call instrumental methods. And the other one is without using the instrument, which is called classical method. For this course, in classical method, we'll be focusing on titrimetric only, titration. However, there are different classical methods. The other one is gravimetric analysis. These methods, they don't use instrument. That's why they are called classical, old method, traditional method. However, in instrumental method, we use instrument. So we use instrument to do the chemical analysis. Some of the instruments, like there are several of them. Some of them are spectroscopy, chromatography, electroanalytical method. For this course, Group D of the inorganic chemistry will be, the part 2 is spectroscopy. So the part 1 is based on classical method and the part 2 is based on instrumental method. Also remember that the course you are currently I'm discussing about is based on inorganic compounds. So just remember the difference. There are organic compounds and there are inorganic compounds. Our focus will be on the chemical analysis of inorganic compounds. Okay. So for the titration, these are some of the, or in general in analytical chemistry, these are some of the general terminologies that you must be familiar with. This is not the part of the course, but you must be familiar with these topics, these terminologies. Sample is the solution to be analyzed. Aliquot is the portion of the sample. Suppose you have a glass of water that you want to analyze. then that is the sample. And from the glass of the water, you might just take 20 milliliter. That will be your aliquot of the sample. And the standard is the solution with known concentration of analyte. And the analyte is the chemical species of interest. For example, in a water sample, if you want to analyze the concentration of sodium, then sodium is your analyte. If you want to analyze this, if you want to analyze the concentration of potassium in the water, then potassium is your analyte. Besides analyte, the rest of the component in the sample is called matrix. So matrix is, in a solution you have, in a sample you have analyte and matrix. If you take analyte out, then the remaining part is the matrix. For example, in water sample, if you want to analyze the sodium, concentration of sodium, then sodium is the analyte. Water is also the matrix. All other ions, all other chemicals like potassium, magnesium, whatever are present in the water, they are matrix. Interfering agents. So interfering agents are the chemicals that interferes the analysis of analyte. For example, if you are analyzing the concentration of sodium, then the potassium, which is just like the sodium, it is the alkali metal. Most of the properties of sodium and potassium are similar. Potassium might interfere the analysis of sodium. So if there are 20 sodium and 10 potassium, whenever you analyze the sodium, you might get the result more than 20. So 20 comes from the sodium, and some of the potassium like 2, 3, or 10, they will also add up into the sodium. They behave like a sodium, so you have result more than what you expected. Sometimes you may have less. So you have sodium and potassium, or so, for example, you have sodium and chloride. Sodium might form sodium chloride, let's say. And whenever you are just trying to analyze sodium ion, maybe there are some of the sodium reacted with chloride to form sodium chloride, then it interfered. The value of sodium gets lower than what is in the glass. The other terminology is precision. Precision is the reproducibility of the result, how reproducible the result is. And just like the precision, there is another terminology, that is accuracy. Accuracy is the closeness to the true value. So precision is how reproducible your result is. You might, your instrument, or you might get the reading 20 ml, 20 ml, 20 ml, then it is very precise. You got 20, 20, 20. However, the 20 is not the, could not be the accurate value. Maybe the 30 is the accurate value. Maybe there was 30 milliliter, but for some reason, your device is not working properly. It gave the same result every time. However, it is not accurate. Could be, okay? Sometimes it could be very accurate and very precise. Some of the results are neither accurate nor precise. Some of the results are just precise, not accurate. Some of the results are very accurate, but they are not precise. For example, let's say you weigh 43 kg, then you might get, sometimes you get 43.5 kg, 43.2 kg, 41.5 kg, like that. They are very close to the 43. However, they are not precise. They are randomly distributed. Selectivity is distinguishing one is chemical species from other chemical species. So you want to analyze the sodium, it selectively analyzes sodium. It does not analyze potassium or any other ion. Like the pH meter, it analyzes the concentration of hydrogen ion. It selectively analyzes the concentration of hydrogen ion. Sensitivity is the smallest change that can be measured with acceptable error. So this sentence also tells you that there are always going to be some types of error in the measurement. So if it is acceptable error that you can measure with the smallest change, then it is the sensitivity. So for example, you have a ruler, the scale. you can measure maybe 1 millimeter with acceptable error. But if you have to measure 0.1 millimeter using the regular scale that we have, then it's going to be not acceptable. The error that you get will not be acceptable because it is not the smallest sense that you can measure with the regular ruler. Though, so now the next terminology is signal. Signal is the desired information, and the other one is noise. Noise is the undesired information. So these signal and noise are like in the classroom, you want to hear what your teacher is talking about. You don't want to listen the other students talking. So that whenever the students are gossiping, that is the noise. And whatever your teacher is saying, that is the signal. So noise and signal you can compare to the, both of them are sound, right? Whatever your teacher is saying is also the sound. Whatever the students are talking is also the sound. But what the information that the teacher gave you is the signal. And the gossip, the sound that comes out from the student due to gossiping is the noise. So similar types of information are also obtained while you are running the instrument or while you are doing the chemical analysis. And the desired information is the signal and undesired information is the noise. So now on, whenever we talk about the chemical analysis, make sure you use this terminology as they are supposed to be. Don't mix analyte and sample. Most of you are confused with analyte and sample. Make sure you know the differences. Make sure which terminology to use. Make sure you use the right terminology. Okay. Now, this is just the brief introduction on the primary standard and the secondary standard. So the primary standard, both of them are the standard, no? So primary standard is very high molecular weight, pure compound, and they are readily available, have lots of good properties. So to be all, not all the standards are primary standards. They need to have very, very good properties like listed here. And there are some secondary standards. They're used, standards used for standardization. Its concentration is found by comparing against primary standard. They don't have, like they, out of these 5 properties listed for primary standard, if one of the properties fails, then it goes into secondary standard. So it is not like you can have 4 right, and if there is 1 wrong, then it is still primary standard. No, you need to have all the best properties that you can ever expect it for primary standard to be present to be a primary standard. If one of the information fails, then it is the secondary standard. Okay. Oops. If you want to practice, then these are some of the assignment. You don't have to. Titrimetric method. Now, still on the introduction part of the titration. So in the titrimetric method, you can have volumetric or gravimetric. So in volumetric, the volume is the signal. And in gravimetric, mass is the signal. And here is the general picture for the experimental setup. You might have done this in the lab yourself several times since your +2 in science, since class 12 maybe. As you can see, it consists of a stand that holds the burette. A burette is a very long apparatus. The burette has level. This one level milliliter, 0, 1, 10, 20, 30, up to 100. So this burette is 100 milliliter burette. The burette has a long neck coming out through which the solution in the burette comes out into the conical flask. And the conical flask, it consists of, here it says the sample to be titrated. And the conical flask is also called titration flask. Okay, so if you understand this setup, then it is the same setup we will do for every types of titration, either acid base, redox, complexometry, or precipitation. Just remember this setup. So there are different terminologies in that setup that we must be familiar with, and maybe these are the common terminologies. Most of you might be already familiar with them. Titrant. Remember the difference between the first word and the second word. One of them ends with T and the other one ends with D. So the titrant is the reagent added from the burette, whose volume is the signal. So basically we drip the reagent from the burette and we measure that volume, the initial volume and final volume. It is usually standard. So whenever you do the titration, there is unknown and standard, like the sample and the standard. And the titrant, the one that you put on the burette, is most of the time standard, not always, okay? It doesn't have to be, but most of the time it's easier if it is a standard. Titrant is the reagent in the conical flask. It is usually sample. So if you know the difference, one ends with T, the other one ends with D. The T is the top, so the top one is called titrant, and D is the down. The down one is called titrant, okay? Equivalence point. So during the titration, there is a point where stoichiometrically equivalent amount of titrant and titrant react. So remember, you are in the chemistry. So stoichiometrically means in the balanced chemical reaction, like in balanced chemical reaction, okay? So whenever there is a, like 2 NaOH reacts with 1 sulfuric acid, right? If they have same concentration. So that's when the equivalent point is obtained for sodium hydroxide and sulfuric acid. End point. So end point is in the titration is when we stop the reaction. When we stop adding the titrant, so you stop the reagent coming out of the burette. It is detected by some physical changes like color change of the solution. Okay, indicator is the color compound whose change in the color signals the end point of the titration. So you are basically adding the reagent from the burette, and when the solution starts to react with the when the reagent from the burette starts to react with the reagent in the conical flask, there will be some color change. And whenever you see the desired color change, that you must be aware of the color change that you are looking for. Whenever you see the desired color change, you stop the reaction. That is end point, and the color change is obtained for indicator. So we'll be discussing about the indicator in detail in later sections. Titration error. So that there is a difference between equivalent point and the end point, and that difference is the error. Okay, here's the formula. So just get familiar with these terminologies. You don't have to memorize them. However, you just need to get familiar with them. Okay, know the differences. So here is the basic principle of titration methods. So titration is the process of determining the quantity of substance A by adding measured increment of substance B, with which it reacts almost always as a standard solution called the titrant, with provision for some means for recognizing or indicating the point, the end point at which essentially all of the A has reacted. So in conical flask, you have A. In burette, you have B. You keep adding B until all of the A is reacted. Not more, not less amount of B is added. Just until A is reacted, okay? So like I said, you have A on the conical flask, B on the burette. You keep adding the B. Here is the tap on the burette. You can open or close. As you open, the reagent starts to drip, and you keep adding B until all of the A is reacted. How do you know when all of the A is reacted? When you see the change in the color of the indicator. So all of the A reacted, then you stop the reaction, or you stop the burette tap, you close the tap. Since you end the reaction, it is called the end point. So you have the initial reading, you have the final reading of the burette. Taking the difference between the initial reading and the final reading, you get the volume of the titrant. You should know the concentration of the titrant, and you know the volume of the titrant. So now you use the normality equation. N1V1 is equal to N2V2, or NAVA is equal to NBVV, to find out one of the unknown in the equation. Okay. So before we get into this topic, let's try to introduce some of these reactions. You are already familiar with most of them. Acid-base reaction is when acid reacts with base. Here is the example of sodium chloride reacting with sodium hydrochloric acid reacting with sodium hydroxide. Sorry. And there is the redox titration where the oxidation and reduction takes place. So here you have iron 2 plus reacts with cerium 4 plus, and the product is not given. However, it is trying to show you that in this reaction or oxidation reduction reaction takes place. Complexometric titration reaction, complex is formed. Here magnesium plus EDTA, you will form the complex. Precipitation reaction, you form insoluble species called precipitate as a product. Like silver nitrate reacts with chloride, you get some sorts of precipitate, and that types of reaction is precipitation reaction. So now once you are familiar with these reactions, the topic that we need to understand are types of titrimetric. There are acid-base titration. Basically, if you know acid-base reaction, then acid-base titration is the acidic or basic titrant reacts with acid or base. So basically in burette and in conical flask, one of them is the acid and the other one is base. And you do acid-base reaction, like these types of reaction. Once you start adding, they starts to react because acid reacts with base to form salt and water. And you keep adding the titrant until all of the titrant is used up, which is indicated by the color change in the indicator. You might be familiar with some of the indicator like phenolphthalein, methyl orange, etc. Those color change will indicate that you need to stop the reaction. That is called end point. Once you stop the reaction, you measure the difference in the volume in the burette, and you use normality equation to find out the concentration of unknown. Now, redox titration has in redox titration you have redox reaction. So you need to have oxidation and reduction taking place. One of them is oxidant and the other one is reductant. So one of them will be in the burette and the other one will be in the conical flask. Like in complexometric titration, you have complex formation between the metal and the ligand. One of them will be in the burette and the other one will be in the conical flask. And there will be an indicator as well, which will indicate the end of the reaction. Precipitation titration is you need to have two species, the titrant and the titrant, to form the precipitate. So basically, if you look into all this titration or all this reaction, there are two reagents, okay, two reagents. They have to react with each other and you must know the chemical reaction beforehand, okay? For example, if you want to analyze the concentration of hydrochloric acid, then you need to have the you need to know what is the other reagent that you are using. Okay. In the redox titration, you have oxidant and reductant. Complexometric titration, you have the metal and ligand. And the precipitation titration, you have these two reagents. Okay. And the syllabus is focused on three of these: redox titration, complexometric titration, and precipitation titration. So we don't discuss about acid-base titration. I believe all of you are have good knowledge of acid-base titration, since as you can see, most, like if you understand acid-base titration, then other titration, it won't be that tough. Okay, but make sure you understand acid-base titration in detail. Other three we will be discussing in detail in coming sections. So what are some of the requirements for titrimetric method? It doesn't mean that you can always do titration to determine the concentration of analyte. There are only certain reactions, right? Not all of the reactions can occur. So the first thing first, you need to know the stoichiometry between the titrant and the titrant. That means you need to know the balanced chemical reaction between the two reagents that you will be using in the reaction. Like in the previous slide, I showed you there are always going to be two reagents. You need to know the balanced chemical reaction between those two. Okay. And the next one is the titration reaction must effectively proceed to completion. So the reaction must be always complete. Okay. There should not be any leftover, because the whole purpose of this titration is to analyze the concentration of the unknown. If the reaction is not complete, then there will be a lots of error, unwanted errors. The reaction should have no side reaction. Like I said earlier, there should not be any interference. If there is an interference, then there is going to be the error. Okay, there should not be any side reactions. The titration must occur rapidly. So as you will be adding the reagent from the burette, as soon as the reagent from the burette goes into the conical flask, the reaction must be rapid. It should occur rapidly. So that's why you need to add dropwise. Whenever you add the reagent, you have to add dropwise. There must be a suitable method for accurately determining the endpoint, like indicator, for example, or there must be an instrument. So for this one, we'll be having indicator. Indicator is the common approach for our course. However, I'll be showing some of the slides where what would have happened if we use the instrument, or how it is measured in the instrument. So what are the requisites of the indicator? So to be an indicator, okay, which will be visual indicators are widely used for an endpoint detection, to detect the endpoint. There should be sharp color change at the endpoint. There should be sharp, okay, from colorless to pink, from yellow to red, like very sharply. There should not be any intermediate colors. The color reaction should be specific, or at least selective. So there should be it should be selective. Like why is the color change occurring? It should be specific, okay? And the color compound must possess sufficient stability. So the color compound that you form must be stable. If it is not stable, then you keep adding the reactant and the reagent from the burette, and you don't know when it will be stable. So you will not get the accurate result. The color contrast before and after the endpoint should be readily observed. Well, since you are observing the color, there should be very clear distinction between the color before and after the endpoint. Like you cannot have some color changes, for example, blue and dark blue. They are very similar. Like how do you distinguish blue and dark blue? You could, but it is very difficult. If it is red and colorless, then it is easy, because one of them is the red and the other one is colorless. It is very easy. Like if you have green and blue, maybe you can, but sometimes it is difficult. So those kind of colors, the indicator with those kind of color is not preferred. So the indicator that you have been using for acid-base reaction, for example, phenolphthalein, it is widely used, so it has a very good color, right? Distinct color, colorless and pink. So those kind of colors those kind of indicators are preferred. So the indicator must be very sensitive to the chemical species to be measured. measured so that the color change occur as near to the equivalent point as possible. So like you have seen the earlier, like titration error, there is a difference between the equivalence point and the end point. So the end point must be very close to the equivalence point. Those kind of indicators are preferred. And it should be, the indicator must work in the pH range of the titration. Let's say 5 to 12, 1 to 14, like those, there should be a certain range that it will be working. And for indicator color change to be detectable by normal eyesight, a rough tenfold excess of one or the other form of the indicator must be present. So what this means is you have an indicator, right? So the indicator is either in X form or Y form, for example, X or Y. So if it is X, then it has one color. If it is Y, then it has another color. Whenever it is in X to Y, whenever the color changes from X to Y, that is the end point. So that color change will be observed when is one of the reagent is 10 times more than the other reagent. That's when the color change is observed. Okay, 10-fold excess. One of the concentration is 10 times the other one. So these are some of the indicators you can look into. You don't have to memorize. In acid base, methyl orange, phenolphthalein, methyl red, they are shown for the analyte and the titrant. For precipitation, there are also the indicators indicated. For complexometric titration, there is oxidation reduction reaction. There are lots of these. So there are several well-defined indicators. Okay, the indicator is not something that you will have to choose on your own. They are all well-defined indicators. Like you can just have to go and find it from the book or find it from some research articles. Then you use it for the types of reaction that your desired reaction. Okay. So what if you use the instrument? If you use the instrument, then you get the graph like this. Okay, there are 4 graphs shown in this slide, and these 4 graphs are for different types of titration. The first one on the top left is for acid-base titration. Then on the top right is complexometric titration. Down bottom on the left is redox titration, and right down is precipitation titration. Now let's look into the acid-base titration. Again, this is not what we will be studying in this course. The other 3 are what we will be focusing in. However, to understand the other 3s, you must be familiar with acid-base. Acid-base. So on the y-axis, as you can see, is the pH, which is the definition for the concentration of acid or concentration of hydrogen ion. And here on the y-axis, there is the volume of sodium hydroxide. This most, like always, the x-axis is going to be the volume of titrant. So the volume that you add from the burette. In this scenario, the volume is of sodium hydroxide. So the base is in the burette. Okay. As you can see, all these drops, we can look into the drops. So at the beginning, the conical flask has acid. Why it has acid? Because burette has base. If the burette has base, then the conical flask must have acid, right? Those are the 2 options for acid base. So the conical flask has acid, that's why the pH reading is less than 7. In this case, the pH reading is about 1. Maybe it's a strong acid. And you haven't added any base till then. It is the initial phase. Now you add about 5 milliliter, because in the x-axis, if you go down this drop on the x-axis, it is about 5 milliliter then of the base, then the pH rises, maybe 1.5. If you add 10, then it rises, obviously, right? Because now you have acid and base reacting to form salt and water. So the concentration of the acid is decreasing. As the concentration of the acid decreases, because it reacts with base, the pH increases. Now you keep adding the base, the pH keep increasing. This is by using the instrument, okay? You are using the instrument to measure the pH. Now at certain point, the rise in the pH is steep. See, before adding, until this point, the pH was about 2.5. Then it goes to 7. Then it goes to 12, about 12. There is a steep change in the pH. And how do you get this pH? From the instrument, like pH meter. Okay, then you keep adding the, now you added the sodium hydroxide, more sodium hydroxide, then the rise in the pH is very small. See, so there is only at this region where the rise in the pH is very high for this small amount of sodium hydroxide. Then what you do? In this steep rise, you draw a vertical line. Okay, if you draw the vertical line, then it will, the point where it coincides with the x-axis, that will be your volume. Okay, that will be the volume of sodium hydroxide required to neutralize the acid in the conical flask. Okay, again, at the beginning, the rise in the pH is very slow. Also at the end, the rise in the pH is very slow. Somewhere in between, there is very steep rise. That steep rise will give you the equivalent point. If you do the vertical line, then you get this volume of sodium hydroxide required for the neutralization of base acid. Okay. Now, if you understand this, then all other are very similar. So here is a pH, here is PCD. This is the complexometric titration. So this is for the hydrogen ion, that's why it is pH. This is for cadmium ion. CD is for cadmium. So if it was calcium, then you will have PCA. You know the difference, right? What is PCD means? Negative log the concentration of cadmium ion. Okay. Now this is not that detailed like in here, because these are what we'll be discussing in future. You have very similar graph. It goes up, up, up. There is a steep rise. And then you have this. You can have a vertical line. Then you get the volume of titrant. So this titrant is from the burette. You have the cadmium in the conical flask. Okay. So this is pH, PCD, and the volume of titrant. Here is also the volume of titrant. For redox titration, however, you will have the potential. Okay. Because in redox titration, there is the involvement of electron, and the flow of electron generates potential, correct? That potential is measured. So at the beginning, there is very small rise in the potential. At certain point, there is a steep rise. Then you get the equivalent point, you get the equivalent volume, and then you can get the concentration of the unknown. So this is also for the redox titration. And you have precipitation titration, which is very similar. You have on the y-axis, you have PCl. So you are measuring the concentration of chloride ion, Cl minus ion. What is PCl? PCl is the negative log of chloride ion. PCD is the negative log of cadmium ion. But pH is the negative log of hydrogen ion concentration. Potential, because there is the electron involved. And on the y-axis, there is the volume of the titrant. It's like what we did in the acid-base titration. The same principle is implemented to get the equivalent point. Okay, so that is all for today's section, and this is just the introduction part. We haven't got into the topic, so the next class will focus on redox titration.